So let's start the class. So in the previous classes we studied what are word vectors and how do we generate word vectors based on the term frequency and point-wise mutual information. So let's summarize that. So we studied vectors based on term frequency or we can say it is actually the counts of words in a corpus with respect to each document we also saw vectors based on positive point-wise mutual information. PPMI, right? Now these vectors had some characteristics that what are the characteristics of these vectors? These vectors are sparse vectors, that is the matrix generated is a sparse matrix of words. So these are sparse vectors and these are also very long size vectors, large size vectors. Right. So these are sparse vectors means that these vectors have large number of zero entries, and large size vector means that they have size is or length of vector is equal to vocabulary size, which is mod of v, right? So if there are 1000 words in a given corpus, so each vector size will be of 1000. Now what we can do is that we can reduce the size using dimensionality reduction. That can be one way to reduce the size. However, we can reduce the size using dimensionality reduction techniques. Such as PCA, SVD, etc. Right? So we saw all these things. We did not saw the dimensionality reduction, perhaps, but it can be done. So we will today see another kind of word vectors that are very powerful in nature and that were introduced by Mikolov in 2013. And we will not see the exactly the Mikolov version of the word embeddings, that is called as word2vec, but we will see some kind of simplified version of those embeddings. So Mikolov used actually the neural networks, but we will not be using the neural networks, we will be using some kind of simplified version with similar to logistic regression. So we will be using, we will be studying now word2vec. Word2vec. So this word2vec actually uses a technique called as skipgram, and it uses another technique that is called as negative sampling. So actually in the original paper of word2vec there were two techniques, one is the skipgram model and one is the continuous bag of word model. So the skipgram model is actually the model in which we consider a word is surrounded by a context. Word is surrounded by many contexts. So we are focusing on the target word, right? But in case of continuous bag of words model, we focus on the context as well. So the aim here is actually the aim. So instead of making some kind of counting or counting probabilities, we would like to train some kind of classifier instead of counting the values or calculating instead of counting or calculating some values, train a classifier so that these values are more refined. These values may be used, but along with the training of a classifier, so these values get more refined, or the values generated by the classifier or the weights generated by the classifier will be more refined, more close to the actual or more powerful. So what is the task here? The task is actually, in a classifier, the task is prediction task. So what could be that prediction task? So we can predict that whether a word is a particular word is in context with another word or not, right? So specifically we can say, is a word likely to show up near the context. See, suppose this a target word P is likely to show up near the context C. So we will be just making a prediction that whether a word T is near the context C or not, right? Or C is the context of T or not. So how would we make this kind of prediction or classification? Actually, we are not concerned with the prediction, but we will use the prediction settings and we will train the classifier, but finally we will not predict the output, but we will use the weights of the classifier as the embeddings. Okay, so we say that, however, we skip the prediction and the weights of the learned classifier will be used as embeddings, right? So for a classifier, we require a training data. So how to generate that training data, or we require, specifically we will say that we require supervised or labeled training data. So how would we obtain this data? Okay, so we have the corpus. So the running test from the corpus can be considered, the running test from the classifier can be considered as the training data. So let's see how. The running text from the corpus. So it may not be a labeled corpus, it may be a simple corpus. Can be considered as supervised training data. So that's the crux of skipgram. So skipgram follows from here. Skipgram follows these steps as at first we need to treat the words and its surrounding or neighboring context as positive samples. So treat the words, so any word and its context pair can be treated as a sample, right? So treat the target word T and its neighboring context C as positive sample, right? Then now the classifier also requires the negative samples. That means a particular word is a context of another word C is a positive sample. so this is a kind of binary classification. So one label is positive, one label is negative. So this tuple or this pair is considered as a positive sample. Now classifier also requires a negative sample, because the classification will require both kind of samples, positive, negative, 0, 1 or something like that. So how to generate the negative samples? That the generation of negative samples is done by the technique called as the name suggests, is negative sampling. So what we do is that here we take all the other words and make the pairs of them. We take the target word T, okay, and we mark the actual context as positive samples, and we mark the rest of the context or rest of the words as their negative samples. Okay, so randomly use the other words in the vocab to obtain the negative samples. So we don't consider all the rest of the words, but we take some of them randomly. Then we train the classifier, and finally we use the regression weights as embeddings. Train the classifier such as logistic regression. So logistic regression is also a classification algorithm, but it is based on regression. So the regression weights can be considered as embeddings or word vectors. So now let's see what is the classifier. So in this classifier we need to train a classifier, such that the pairs, or we call it a tuple here, the tuple T comma C, okay, generates the probabilities as P of positive given T comma C, right? So it will generate two probabilities, positive probability and the negative probability. So and we can also calculate P of negative given T comma C as 1 minus this probability. Right, so these two probabilities will be generated. Positive probability will be generated, but what we will use in place of T and C, because we require some kind of numerical values in place of T of C to use it in these probabilities, or some kind of categorical or real values. So what we need to do is that we need to actually replace this tuple with its similarity score. Okay, so this classifier would compute the probability not by using the tuple but using the similarity score. So what our aim becomes is that a word is a target word is likely to appear near the context C, or simply the context, if its embedding is similar to the context embedding. So we saw in the previous classes also that the embeddings are in vector spaces, and if the two words appear near to each other, then their embeddings in space will also be near to each other. So near to each other means that they will have a very large value of the cosine similarity, right? So a target word is likely to appear near its context if its embedding is similar to, but we don't have the values of t and c or any vector in the form of t and c. So each of this t may be now assumed as a vector or a random vector, right? So each of these, so this similarity of t comma c is used in place of t dot c actually. So t dot c is the dot product, right? So similarity we know is the dot product. So the probability of positive given the dot product of t and c, or we may write as the probability of positive given some kind of, we need to bound this probability, we need to bound this similarity score between 0 and 1, right? So this is actually between minus infinity to plus infinity. Right, so this similarity score is between minus, so we are not using the cosine similarity here, but we are using the simply dot product, so which is actually between positive infinity and negative infinity. So what we need to do is that we need to bound this with some kind of function. So we bound this similarity using the logistic function. So this logistic function is a function that is of this form. So this is the logistic function. Okay, so we can bound this probability. Now what this function does is that it actually takes the value as input is x. So this x can be somewhere between minus infinity and plus infinity, and it generates the value of sigma x, which is between 0 and 1. So it is like this. This is So this is the logistic function which is used in logistic regression. So this classifier is working in the same way as the logistic regression. So this is the values of x, which are minus infinity, plus infinity, and this is 1, this is 0, and this is 0.5. Or we can slightly modify this function, and we can bound the values between -1 and +1, right? So in this way we get this positive probability, the positive probability as this p of positive t given c is, by using the logistic function, becomes 1 upon 1 plus minus t dot c, where t dot c is the dot product, and instead of dot product we will be treating it as a similarity score. So and this negative probability, so these two probabilities will be calculated in this way now, right? So and these probabilities are calculated for all the samples, right? So how do we get the samples? Let us see. So as an example, there may be lot of words present in the corpus, and from that corpus we can obtain these kind of samples, right? So apricot is in context with tablespoon. This is a positive sample. Yes, apricot is in context with off. Apricot is in context with jam. But apricot is not in context with aardvark. So this is randomly taken with apricot. Aardvark is randomly taken as a context with marked as a negative sample, right? So in this way, from the whole corpus we can generate a lot of samples for all the words that are present in the corpus. Now for all the words we need to generate some kind of we need to train the classifier. So how would we train the classifier? In order to train the classifier, we require some kind of loss function that has to be either minimized or maximized, right? So just before that, let's see how this dot product is working. So we have this t dot c, right? So this t dot c is actually, suppose t is a vector, random vector. I have taken some random values. This is t here. I have taken a vector with some random values. Okay. Suppose size is d here. Okay. I have taken c as some random vector of size d. This size is this can be defined while training the classifier. It can be 50, it can be 100, it can be 200, 300, and let these values are t1, t2, and so on, c1, c2, and so on, right? So the dot product can be written as t1 dot c1 or t1 star c1 plus t2 star c2 plus dot 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 td star cd, where t1 comma t2 dot td and c1 c2 dot 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 cd are randomly generated values. So for all the positive and negative samples, these kind of vectors will be generated randomly. So that is called as the initialization of the classifier, right? So all these values will be generated randomly. So the probability of all the samples, or let's take the probability of a word, a target word with all the context can be written as like this. So P of positive given C1 colon K can be written in this way. P of positive given with all its context, right? So that can be written as a product of all these logistic functions of all the pairs of P with Ci. So why we are taking the product? So since all the context words of target word are independent of each other, we can multiply the probabilities. So that's called as the conditional independence. So if some variables are independent of each other while calculating the total probability, we may multiply all the probabilities together, right? So now what we can do is that we can train the classifier with some loss function. What is the loss function? The loss function is the loss that is generated by the positive samples and the loss that is generated by the negative samples. So one loss is for P of T given C, and we are having the log probability. So in case of log probability, we don't need to multiply, we can just sum up all the values here. So in general, we always use log probability of or log of the values. Wherever there is a product of terms, we may convert it into the sum of terms. So this loss function becomes loss theta is equal to summation of log probability of positive samples and summation of log probability of negative samples, where in which each of these T comma C tuple belongs to the positive and the negative samples. So the goal of classifier training, so while training, the goal is to, number one is maximize the loss of positive samples and minimize the loss of negative samples, right? So we require, while training, what we need to do is that we require some kind of loss function. Okay, so this loss function, in general case, the logistic regression has only has this loss function, right? Similar to this loss function. So where we need to maximize these log probabilities, the summation of log probabilities. So in order to maximize the log probabilities, we will be using the similarity score in place of this tuple, and each similarity score of each word will be having some random values. So each of these T and C pairs will be actually vectors with some random values. So those random values that were assumed here, so these will be now trained, or these will be gradually and slowly in learning, they will be trained to the most appropriate values, right? So after the learning, when we maximize and minimize this goal, now collectively we apply this goal while training. So we will, these values of the vectors T and C for each word will get changed. So how does that get changed is actually we apply some kind of optimizing function or optimizer. So we may use some kind of optimizer like gradient descent. Optimizer like gradient descent may be used to train the weights, to optimize the weights. Optimize the weights, or specifically the randomly generated embeddings, right? So here these are actually the T vector and the C vector are the embeddings, and these were initially randomly generated. Now these will be gradually and slowly, with the help of some kind of optimizer like gradient descent, these will be converted into the actual embeddings. And now these embeddings will be treated as the word embeddings that we require, right? So this will be done for all the words and for all the contexts. So this loss function is having T comma C belongs to all the positive samples. So all the positive samples will have all the words and context. Similarly, negative samples will have lot of words and context. So we will cover all the target words with their positive context, but with some negative context, right? So in this way we will obtain the embeddings, right? So optimizer is a kind of it actually finds out the optimum value of the parameter. It either maximizes the value of the parameter in a given function, or it minimizes the. So we use gradient descent or gradient ascent or other optimizers, such as a very popular is there are latestly they are very popular, like Adam and all. These are used in deep learning. So these are also optimizers. So we may use a simple one, gradient descent, just to, because we are having a simple loss function here. So after training we will obtain the weights which are in the form of embeddings, and we just skip the prediction part. We do not require any prediction in this case.